Welcome to a new AG session all about analytic geometry. This time, we are going to prove that a triangle that can be formed using the points A, which is negative 2, 4, B, negative 5 and 1, and C, negative 6 and 5, will be forming an isosceles triangle. Considering this Cartesian plane, we could of course plot these points considering that upper grid is 1, and of course we know that the horizontal axis is the x-axis while the vertical is y. So point A can be found at negative 2, 1 is 2, that's negative side, and then we have 4, 1, 2, 3, 4. This is point A at negative 2 and 4. The next point is B, negative 5 and 1. So you have negative 2, negative 3, negative 4, negative 5, and you have here 1. This is our point B. And our point C is negative 6. You have here negative 6 and positive 5. So 1, 2, 3, 4. You have here just 5. This is point C. So of course, if we're going to connect these 3 points, we could come up with a triangle. But the concern here is whether the triangle is isosceles. To do that, let's remind ourselves that an isosceles triangle is a triangle where 2 of its sides have equal measurements. So if we're going to connect all these 3 points, you will be forming triangle ABC, BCA, CAB. It's up to you what you call it, this one. We have here triangle ABC. Of course, its sides would be side AB. Okay, this is the correct notation. You have side BC, and you have your segment AC or CA as another side. For an isosceles triangle to be formed, we need to show or prove that exactly two of these 3 sides will have the same measurement. Okay, only 2 of the 3 sides. We can show that by solving for the length or the measurement of the length of the segments AB, BC, and AC using this distance formula. You have from point 1 to point 2, and you're solving for the length of that. This could be solved using this distance formula. You're going to take the square of the difference, x sub 2, x sub 1. You square that, plus that will also be for our y values, y sub 2 and y sub 1. You take the square and you take the square root of that. You will get the distance for each. Of course, you could always rewrite y sub 2 and y sub 1 here first, and you could even interchange x sub 2 and x sub 1 here, saying x sub 1 minus x sub 2. Doesn't matter as long as you're squaring it. But please remind yourselves that if we're going to show here x sub 1 minus x sub 2, the other values will also be interchanged. Now let's try to solve first. This is the segment or the distance of points A and B, or the distance of the line segment AB. Let's pick point B as our point 2 and point A as our point 1. So our x sub 2, that's the point for x sub 2 for B. You have negative 5, okay, minus our x of our A, negative 2. Please don't forget to enclose it in parentheses so that you could actually apply the correct operations. Plus, you will have here for your y. Take note that we started with B as our x sub 2. So our y sub 2 is 1 minus our y sub 1, which is 4. Or you don't need to have parentheses here because it is positive 1 minus 4, and you take the square of it. So you will have here the expression. You have negative 5 plus 2, that's negative 3, and you take the square of that. Plus, on the other side, you will also have negative 3, and you square that as well. This would mean you will have here, that's 9 plus 9. In short, the distance for points A and B, or the measurement of the line segment AB, is equal to 9, I'm sorry, it's not 9, it's 3 square root of 2. applying the rules and laws of radicals, you have 3 square root of 2. You might want to review that as well. This is distance, or you could of course write it as square root of 18, but this is a simplified form. Now let's proceed to BC. Same process, but this time we will be picking point C as our second point. So our C, our x sub 1, x sub 2, because we pick C as our second point, so it would be negative 6, that's x sub 2, minus x sub 1, which is, we have here negative 5. So you square that. Plus your y sub 2 for C is 5, minus y sub 1, which is 1. Okay? And square that as well. So we'll have here square root, that's negative 6 plus 5, that's negative 1. You square that. Here, you have plus, of course, you have 4 squared. You will have here a result of 1 plus 16. 16, that's 16. This is equal to square root of 17. And since 17 is a prime number, it doesn't have any perfect square factor aside from 1. That's the result. Take note that earlier, this is actually square root of 18, right? They are just close to one another, but they are not equal. So we still need to verify the last line segment, okay, or the distance between A points or vertices A and C. And let's see if this could be similar to either of the two. So we have here, let's pick C as our point 2. So you have negative 6, that's enclosed in parentheses, minus your x sub 1, which is negative 2. You square that, plus your second, for your y sub 2 is 5, and you have here minus 4. That's your y sub 2 as your y coordinate of your A. So this is equal to, so you have here negative 6, that's double negative property becomes plus. So 6 plus 2, you have negative 4. But you will be squaring that. Plus, on the other side, you will have here 1 squared. You will have here the square root. That's 16. 1 squared is 1. So you have here a result of square root of 17 as well. So we could see here that two sides, side BC and AC, in short, this line segment that if drawn connecting to these two, and AC will have the same distance of square root of 17, and our AB is just square root of 18 or 3 square root of 2. This proves that this distance, BC square root of 17, is the same as, or has the same length as AC, which is square root of 17 as well. And the third side, AB, is just square root of 18, so they are not the same. This triangle with this 3 vertices A, B, and C is considered as an isosceles triangle. Thank you for watching, and stay tuned for another session here in AG for Analytic Geometry.